Welcome everyone to this Monash Cybersecurity Seminar. Today we are happy to welcome Michael Reichle, who is a PhD student at École Normale Supérieure and INRIA under the supervision of Bryce Minow on the topic of searchable encryption. So he is further interested in a wide range of cryptographic areas such as zero-knowledge proofs, range proofs, or anonymous credentials. And today Michael will talk to us about efficient range proofs with transparent setup from unbounded integer commitments. So thank you, Michael. The scene is yours.
Thanks. So, share the screen. Okay, perfect. So thanks for the introduction and hello everyone. So yeah, as already said, I will talk about range proofs today, and more specifically about how to construct efficient range proofs with transparent setup from bounded integer commitments. So this is essentially a talk about the paper from Eurocrypt 21. And yeah, first of all, my name is Michael Reichle, as already said, and this is joint work with Geoffroy Couteau at IRIF and CNRS, and Michael Kloos at KIT, and Wang Lin at Mercury Swing and Sutosu. Yes, so let's just dive right into it. Let's just dive right into the topic. So first of all, what are range proofs and what are they useful for? So a range proof is essentially just a way to show that a hidden but fixed integer lies inside a given range. So for example, if you want to show something about a balance that you have in the area of cryptocurrencies, so say the balance is hidden but fixed, and you want to perform a transaction based on that hidden balance, essentially a range proof allows you to do that. And I'll just quickly go over the intuition of how you proceed. So one pirate wants to buy a boat from the other pirate, and so the pirate says, okay, yeah, but I can't see your balance, so how would I be sure that you can pay me? And then the other pirate can just say, okay, I have enough money. Here's a range proof that certifies that my balance lies inside the range, such that I can still buy the boat, so that I can perform the transaction and still have more than zero crypto money. And then the pirates can just perform the transaction on the hidden balance homomorphically, for example, and then everyone is happy. So far for the basics. So that's essentially how we, that's essentially one of the use cases of range proofs. And yeah, essentially in all kinds of privacy preserving technologies, this can be quite useful. And especially if you want to be practical, then this should be as efficient and fast as possible. So how do we practically construct such a type of scheme? So first of all, the hidden balance would be represented by a commitment scheme. So a commitment scheme is just a way to fix and but at the same time hide a value. So more formally, we have a commitment C to a value or a message X with randomness R, which I always represent during the talk with a blue box around the message and the randomness. And we can send an opening to a verifier. So the opening consists of the message and the randomness, and then the verifier can just say, yeah, I trust you, or I don't. And this is a wrong opening. And for this talk, we need, in general, commitments have two properties. So the hiding property, which means that the commitment does not reveal anything about X, about the message. And the binding property, which means that it cannot be opened to something else than X. So this means that X is actually fixed by the commitment. So this is kind of these are the general properties of commitments. And if we want to, so for this talk, we need three more properties. First of all, at least in the beginning, we want that the message space of the commitment is set Q. So that means that we can commit to integers modulo Q in the message space. And also we need homomorphy, meaning, so first of all, additive and scalar homomorphy, which just means if we have a commitment to X0 and X1, we add the commitments with some homomorphic operation on the commitments, then we can get a commitment to x0 plus x1 without having to reveal any information about the committed values. And the same with scalar multiplication. So we can just multiply a scalar n to the commitment, and then we get a commitment to n times x. And yeah, during the talk, I will generally assume that these properties hold for our commitment scheme. And yeah, and I will keep it fairly abstract or like very general for now. So I make no other assumptions about the commitment scheme in the beginning. I will essentially only, I will only go into details later on when I talk about a specific setting. But for now, yeah, this will be the commitment scheme that we will work on or work with. So the next thing for range proofs is that we actually need to show something about this committed value, and we don't want to reveal the message. Otherwise, we can just send the message, but then it's not very privacy preserving. So for this, we generally use zero knowledge protocols or zero knowledge proofs. And in this case, so for our paper, we only use Sigma protocols. So 3-step zero knowledge proofs, which are essentially so a zero knowledge proof is essentially a protocol that can prove to a verifier that has access to a statement X that the prover knows a witness W such that satisfies the statement X. So yeah, and you can think of the statement and the witness as being part of like an NP relation. So yeah, and informally, these types of Sigma protocols are generally built in the same manner. So in the first step, the prover generally commits to a mask of the witness. He sends the commitment to the verifier. Then the verifier draws a random challenge gamma. And then the prover will mask the witness, also include the random challenge in the masking process, and then send the result to the verifier. And then the verifier can check with the first and the last flow whether he's actually convinced or not. And for this to make sense, we need two properties. So the first one being zero knowledge, we want to preserve privacy. So we want that transcripts can be simulated without knowledge of W. And so this is the technical notion. A bit more intuitive. So the intuition behind this is that if we can simulate a statement, if we can simulate a proof without actually having access to the witness, then the verifier can just compute a transcript. So the message is alpha, gamma, omega himself, and he does not actually learn anything from the interaction with the prover, because if he has access to the challenge before, then he can just pre-compute everything. So that's why the verifier does not learn anything from an interaction. And then the second property is soundness, which means that this proof should still, I mean, even though the verifier can't learn anything about the witness from the prover, the verifier should still be able to trust the prover afterwards that he actually knows the witness. And this can be formalized by demanding that we can actually extract a witness W from accepted transcripts where the challenges are differing. So these are the basics for Sigma protocols. And now, because we're talking about range proofs, we want to show something about a committed value. And for this, we need to show that, first of all, we need to show that we know the opening of the commitment. Otherwise, we cannot show anything about the committed value. So I want to go into slightly more depth here about how we can show the proof of opening, because this will become very important for the construction later on. It's essentially, I guess, 3/4 of the range proof or even more. So, so first of all, we have our prover. The statement is the commitment, and the So the verifier also has access to the commitment, and the prover in addition has access to the witness, with this, which is the opening of the commitment, so the message X and the randomness R. And now the prover commits to so first of all, he draws two random masks, a mask for the message X, and so the mask will be called M, and a mask for the randomness R, which we call S. And then we commit to both masks and send it to the verifier. So the verifier receives the commitment D, draws a random challenge gamma, and sends it to the prover. And then the prover computes, essentially masks the value gamma times X with the mask, and similarly with the randomness, so gamma times R plus S. And then we send it to the verifier, and then the verifier can check whether so remember that the commitments are scalarly and additively homomorphic. So we can just, as a verifier, check whether this linear relation also holds inside the given commitments as such. And yeah, so this is essentially how the zero knowledge protocol works, and for the proof of opening. And first of all, it's quite easy to see that it's zero knowledge because we just sent a commitment scheme that intuitively is hiding. And we also send two integer values, Z and T, but both of these are masking the witness. So informally, I think it's quite clear that this should be zero knowledge, and indeed it's also not that hard to prove. Binding is also not very hard, soundness is also not very hard to show, but I still want to go into a bit more detail because it's actually quite important to have a decent intuition about how this works to understand deconstruction later on. If we want to prove soundness, we need to construct an extractor from honest transcript. So we need to extract something from honest transcript. So as a reminder, the statement is the commitment scheme, and the honest transcript is the commitment to the masks, the challenge, and then both masked values Z and T. So let's just say that an adversary can output two such accepting transcripts where the first flow is the same, and then the challenges differ, and Z0, Z1, T0, T1 might be the same, might differ. So now we need to show that we can actually extract from these informations an opening to the commitment C. So first of all, from the verification, the verifier checks both of these, like for each transcript separately. The verifier would check these relations, so whether the linear relation between the witness, the mask, and the challenge hold inside the commitment. So we know that this will hold for honest transcript, or for a not necessarily an honest transcript, but an accepted transcript. I should have written accepted transcript. So yes, so this is what the verifier checks, and now we can just subtract the right side from the left side, and we get this equation. So something times the commitment is equal to a commitment where we actually know the committed values already. And now if we just divide by the scalar in front of the commitment, we get this equation. So the commitment is equal to Z0 minus Z1 divided by gamma 0 minus gamma 1 mod Q, and then some randomness where we also know the values. So essentially we know, so this is how we can reconstruct an opening of the commitment, because yeah, now we know that X will be equal to this in ZQ. So this is how we can extract, actually from this proof of opening, we can extract the committed message. So, I mean, for some, this might be a bit complicated, for some not, I'm not really sure, but the most important bottom line is that is written in yellow. So it's important that from the proof of opening, we can extract X equal to a fraction in ZQ, essentially. So far, so good. Now that we understood how how to prove an opening. I'll go into more detail about range proofs and how to construct them. So essentially, a range proof is just a pseudo-knowledge protocol for the following relation. And so essentially the witness being X and R, so the opening, and the statement is the commitment, and two integers A, B, which define a range. And we want to show that the committed value lies inside the given range X, so X in AB, essentially. So the first approach on how to construct this is probably also the most common approach in literature. So what we do is we decompose X into its binary digits, and then we can show that X is in 0, 2 to the power of L, if X is actually equal to the binary composition, and all the X, like all the Xi's, so the bits of the decomposition are actually in 0, 1, so they are actually bits. And this way we can only represent values from 0 to the L. So it's quite, so yeah, it's obvious that if the decomposition holds and if Xi are actually bits, then X is in the given range. So also, yeah, so in order to construct the range proofs, what you do is you can commit to the decomposition, and then you prove that all your Xi's are inside, so all your Xi's are bits, so either 0 or 1. This is also very easy to show. So essentially, this approach is the most common one in recent range proof literature. So also for the lattice setting, for the D-log setting, because it can be optimized very, very far. So you get very efficient range proofs from this type of construction. The second approach I want to talk about.
Michael, can I just quickly stop you? There is a question. I can read it from Benedict Wagner. For the honest verifier zero knowledge of the proof of opening, do we need a trapdoor for the commitment to show it?
No, we don't want a trapdoor. So I mean, all of this just works with, I mean, everything that we have here is just a commitment, any type of commitment scheme. We don't need a trapdoor for the commitment. And here then we can just perform these calculations, and in the end we get that we can extract X in this way. So it might depend on this might depend on the concrete commitment scheme, on how we prove soundness, how we prove binding, whether how we prove binding, how we prove hiding, whether or not the commitment scheme has a trapdoor or not. But in our case, we generally, so I will come to this a bit later. So we want to use this in privacy preserving technologies. So we generally want to avoid having trapdoors that can be set up with like a nothing up my sleeve method. So for example, maybe in the proof you need that if you have groups, that your generators are set up in a certain way, but yeah, nothing really special, nothing like an RSA trapdoor or something similar. Is that sufficient?
I think so, yep.
Okay. So yes, so for this approach, this approach is a bit different than the binary decomposition approach. So we want to show that X is in a given range AB. I mean, by first of all applying the definition of intervals. So we want to show that X minus A and B minus X is bigger or equal to 0. And actually the important observation is that B minus X times X minus A can actually be decomposed as 4 squares, as the sum of 4 squares. This is a number theoretic result from quite some time ago. And actually, if we decompose it is this way, because I mean, only if b minus x and x minus a is positive, of course. And if we have a decomposition as such, we actually can follow that the left side is positive or non-negative, because the sum of 4 squares is non-negative, of course. But this only holds over the integers. So only if we have a composition over the integers. So for this, we need integer commitments. And in general, these are built over RSA or class groups with trusted setup, and they require quite large parameters. So yeah, the last 2 points are something we want to avoid, but still we want to try to make this this square decomposition work with without these stronger assumptions. So first of all, how we kind of simplified the equation a bit, because it gets easier. Like, it doesn't matter too much for the result, but it just gets easier to read and to understand. So I also applied for the talk. So essentially, instead of showing that x is in a b with the decomposition as before, we just show that x minus a is in 0 b minus a, and then we can just have one range variable, capital B, and we show that x times b minus x is equal to the sum of 4 squares. Yeah, and again, if the right side is non-negative, I mean, if we have equality, then the right side is non-negative, and we have the range. Yeah, we have the range. We have shown that x is in the range, essentially. And now there is one optimization, which was already used in a paper from Jens Kroth in 2005 in AsiaCrypt, I think, which states, so first of all, we know from number theory that each integer that is equal to 1 mod 4 can be decomposed as a sum of 3 squares. And because of that, we can now use only 3 squares. And in order to enforce that we have a value equal to 1 mod 4, we just add 1 to, we just multiply x times b minus x with 4, and we add a 1 in the beginning. And this will still imply positive non-negativity over the integers. And thus we know that x is in 0b. Yes, so far for the basics. I guess if there's any questions about the preliminaries, then this would be the perfect time for this. Otherwise, I would dive into the construction. So the setting in which I present our range proof is essentially we use generic commitments that have the properties that I mentioned in the beginning. So we have the message space mod Q, and they have additive homomorphic and scalar homomorphic properties. And yeah, we want to show for the commitment Z0, which is a commitment to X0 mod Q, R0 that X0 is inside a given range. And yeah, we need some, so X0 is mod Q, so we need to represent, we have an integer representation for this. So we just represent the integers mod Q via Q half, minus Q half to Q half, positive Q half. Yes, and then we want to show that X0 is, for example, in the interval 0, 8, for example. And then also the goal is we want to avoid trusted setup. So we don't want to make use of RSA or class groups that have trusted setup. So class groups don't generally have trusted setup, but if you set up a class group with trust, like with a trusted setup, then you have different properties, which are a bit stronger, or with which you can easier construct cryptographic protocols. So we want to avoid this. So this is why, for example, this generic commitment, you can just use Pedersen commitments. I come to that a bit later, but if you want to think of some concrete commitment, you can just use Peterson commitments, and everything will work out fine, and there you don't have trusted setup. And we also want to optimize efficiency. So yeah, we want to come out with competitive range proofs in the end. So this is the goal. And so I will show the construction in a few I will show essentially how the construction evolved. So the first idea is to just use the 3-square decomposition in ZQ. So we decompose 1 plus 4 times x0 times speed minus x0 as the sum of 3 squares. And we just construct a sigma protocol that shows this relation. And then we see what we get from this. So first of all, how do we construct the sigma protocol? At first, we need to commit. So at first, of course, we need to compute the decomposition. Then we need to commit to the values xi from I to 1 to 3. And essentially, then we send the commitments to the verifier, and then we also choose random masks. So the masks that I showed you in the proof of opening protocol, and then we commit to them in the DI and send it to the verifier. So now the verifier has access to the commitments to x0, so the value that we want to prove the range for, just from the statement, and also the C1 to 3 from the decomposition because we just sent them, and then also for the masks of each for the masks from the proof of opening based on what we just sent also. So these are the DIs fixed in the commitments, and now the verifier just draws a random challenge again, and the prover. So sigma is the security parameter. So to have soundness, so one-shot soundness, we need gamma, so the challenge to be drawn from the range 0 to the gamma, to the sigma, so security parameter. And then we send gamma to the prover, and then the prover again constructs the linear relation between witness, challenge, and mask, sends it to the verifier, and then you can just check for each of the commitments whether the linear relation holds. So this is essentially a proof of opening for the main commit. So for the main commitment, so the commitment C0, and also the commitments to the decomposition, so x1 to C1 to C3. And then additionally, we need to check the 3-square relation. So this I left a bit unspecified because it depends heavily on the setting. But it's not a lot of overhead. So in general, you will not have, so the 3-square relation is, it's not for free, but it's not very expensive compared to showing opening of all the commitments. This is essentially the main or the heavy part of the range proof. So yeah, just to repeat, what we have constructed now is a range proof that shows the 3-square decomposition over ZQ. So the question now is, are we happy or are we not? And the obvious answer is, because this is approach 1, we're not happy because the 3-square decomposition in ZQ does not actually imply non-negativity, because even negative numbers in ZQ can be squares because we have overflows, and thus any negative number can even have like a 1-square decomposition. Not any negative number, but any square root in ZQ can have non-negative, so even negative square roots can have a 1-square decomposition in ZQ, and thus also obviously a 3-square decomposition. So we have no information about whether or not the decomposed integer is actually positive or negative. This is of course a problem because that's what we wanted. This is what we need for range proofs. we want to have information about positivity or negativity. So how can we adapt this? So the main idea is we want to avoid overflows by ensuring a short witness. And then if we have short witnesses and no overflows, then we know that the 3-squared decomposition actually holds over the integers, because the only way that the integer and modulus calculation differs is by actually having if something overflows of the modulus, then in normal integer computation, of course, we just continue calculating, but mod q, we just we calculate mod q. So if this never happens, so if there's no overflows, we actually are exact over the integers, and we're happy. So the idea is everything in the 3-square relation we want to keep short. So for this, we need to keep essentially zi short, because this is, or we need to keep xi short because this is the part of the decomposition, but the verifier only has access to xi by within zi. So he only has access to zi, and in zi we have essentially xi behind a mask. So this is the only value that the verifier can check shortness for. So yeah, so we just added shortness check from the verifier. I mean, short is kind of relative to the modulus, and it should be, it should be, I guess I will come to it a bit later on how short it really needs to be, but intuitively it should be quite a lot shorter than the modulus. So a constant times shorter does not suffice. So this approach, does it work or not? And again, this approach too, so it doesn't work yet, because what we extract, so this is why I wanted to show the proof of opening before, what we extract is actually x0, which is equal to z0 minus z0 prime divided by gamma minus gamma prime. So we saw before that we can actually extract a fraction mod q, which will be equal to x0. And even if we, I mean, by construction, gamma will be fairly short. So gamma is equal to 0 times 2 to the sec-power. So this can be kept short if we keep the modulus large enough with respect to the security parameter. And then zi also depends on the bounds and the security parameter, etc. But also this can be kept short because we do the check as the verifier. So we know that even z0 minus z0 prime divided by gamma minus gamma prime are short. But even though these are short, we multiply with an inverse. So we don't multiply with gamma minus gamma prime directly, but we inverse it before. And inversion mod q does not actually retain shortness. And this is quite easy to see with a trivial example. So for example, we have 1/2, which is always equal to q minus 1/2, q plus 1/2 mod q. So it's quite large over compared to the modulus already, even though it's like 1 and 2 are really small, obviously. So yeah, this approach doesn't work yet. So but the main idea now is that we already know that that the numerator and the denominator are short. So there should be some way to use this fact, the fact that both are short, in order to retain something short. And the core idea is now that we can actually map these fractions in set q to integers via a division in q. So what I mean by that is, instead of mapping 1/2 to just 1/2 mod q, which is large, we just apply so instead of computing mod q, the fraction, we just compute 1/2 over q. So this will be 0.5. Then we round it to the closest integer, which is equal to 1. And this will be trivially small if the denominator and denominator are small, because division in q actually preserves smallness. And this is essentially the core the core technique that allows us to construct efficient range proofs. So what we do, so I mean, the main problem is, of course, we can't just say, okay, we prove the range for this. So for this value, but we keep the commitment unchanged, because we actually need, I mean, what we need to do in practice is we need to show something about a committed value and not about something else, just because it's convenient for us. But if we actually adapt the commitment scheme such that this encoding is actually interpreted as the committed value, then we can actually show, then actually essentially the committed value will retain shortness if both parts of the opening are also short. So in practice, what we do is we relax the commitment scheme such that if we have an opening, so we have a commitment mod q to z times gamma to the power of -1. So this is the old commitment scheme. And we relax it in such a way that it commits to x, which will be equal to z divided by gamma. Division over q, and then rounded to the closest integer. So yes, so this is the way we relax the commitment scheme. And so first of all, it has a lot of nice properties. The first one being if z and gamma is short, then we know that, so parts of the opening are short, then we know that x, so the committed value, is also short, which I hope I have motivated enough. Is very important to use the 3-square decomposition over ZQ. Then also it retains restricted homomorphic properties. I'll go into a bit more detail later on what I exactly mean with restricted. It's a bit, it's a bit hard to go into detail now, but I go into detail a bit later. But essentially all that is important is it has enough homomorphic properties to make the range proof work. Also, it retains shortness. So this I've already shown as well. And importantly, honest commitment remain unchanged. So an honest commitment, we say that gamma will be equal to 1. And then this is just a commitment to x mod q. So this is how we constructed bounded integer commitment schemes. And now we can use these. First of all, I wanted to quickly show binding to give a bit more intuition about how why shortness why shortness is important. So in order to show binding, we just have two commitments that are equal. And
excuse me?
Yes.
Can I ask a question now?
Yes, of course.
It's about the commitment scheme itself.
Yes.
So the domain of x cannot be like really z now, right? Because if z and gamma are short, you will get a restricted number of integers, right?
Yes.
You cannot like go very large x's. You cannot commit to large x's.
Yes, that's a good point. So this is what I mean by thanks for the point. This is what I mean by a bounded integer commitment scheme. We cannot commit to essentially all integers. We can only commit to integers that lie inside a given bound. So this bound is generally restricted by the size of the group or by the modulus, essentially. Honestly, we can still commit to all integers that lie inside the bound that we set up the integer commitment for. But as soon as the integer that we need to commit to is too large with respect to the modulus, then this approach won't work anymore. Because then again, we will have overflows, and this will just lead to a lot of problems. So essentially it's important that all the integers that are committed to are inside a given bound. This is why it's only a bounded integer commitment scheme, because you cannot commit to any x. You can only commit to x inside a given range.
Yeah, thank you.
Okay, perfect. So and I think this is also clear if we show binding. So for this relaxation to be a commitment scheme, we need it to be binding. So how do we prove this? We have two commitments to to some values, and inside the commitments we have some z0 times gamma 0 to the power of -1 mod q, and z1 times gamma to the power gamma 1 to the power of -1 mod q. And the only thing that we know is that these are equal as commitments. And based on this, we already know that because the original non-relaxed commitment scheme has actually the binding property, we know that these values will be equal mod q. So what we can do is we can just multiply with the inverses, and then we get this equation mod q. And because all of these values are short by the requirement of an opening of the commitment, we actually get equality over q. And by equality over q, we can just divide by gamma 0, gamma 1 again, and we get equality for the rounded integers. And here it's heavily important that the values that we commit to are actually short compared to the modulus. So with respect to the modulus, we need shortness. Otherwise, the commitment scheme is not even binding. So yeah, but I hope this conveys a bit of intuition about how we can actually use these shortness guarantees in the range proof. So yeah, and essentially this is approach C. We relax the commitment scheme because honest commitments remain unchanged. We can just use the same range proof as before. And yeah, and in the end, we will extract a value mod q from like just as before. And this essentially in the commitment scheme is mapped to this integer, which is in Z, which is short. And for this integer, also the 3-square relation will then have no overflows because everything inside the 3-square relation is short. And yeah, so this is essentially how the range proof works in the end. And yeah, so this is essentially the construction. And now I just want to go into a few details about about the settings and how to and a few optimizations.
Can I ask you a question?
Yes.
Could you go back to the previous slide? So when you check this 3-square relation,
yeah,
do you do the operations mod q, or are they just over integers or q?
What I show is I show that the 3-square relation holds mod q, and the important part is that all the this is a bit hard to convey in the presentation, I feel like, but essentially what happens is we as in the binding proof, we just multiply with the fractions mod q with the inverses. Then we have like a relation that also only has where everything is essentially short integers mod q. And thus in the relation, we don't have an overflow. So the 3-square relation kind of adapted has no overflow mod q. So it holds over the integers. And then we can just divide again by the challenge. So by the challenge difference, gamma minus gamma prime. And we can floor the we can round the integers again. And then you can see that this, like even the 3-square relation mod q, if the values are short, if the denominators are short for the extracted values, that this even implies positivity for this rounded integer. It's not like 100% obvious, but it doesn't require any hard maths. It's just it's a short computation that you still have to make sure that it works. But yeah, if you're careful, you can see that even the 3-square relation mod q implies positivity over the integers if everything is short inside of it.
Okay.
Yes. So yeah, just quickly now to the decomposition. So I've said that the main part of the range proofs are essentially proofs of opening. So yeah, in order to show the decomposition, we need to commit to it first, then we need to prove knowledge of an opening. And in the D-log, lattice, and class group settings, so these are the 3 settings for which we instantiated the framework. In these settings, we need 1 additional mask, so 1 additional integer to send to verify, and then in the latter setting, we also need an additional commitment to send. So yeah, so this is essentially the overhead that we have to pay if we want to show the decomposition. So it's not a lot, as you see. Yes, and now I want to go into two limitations quickly. So the first limitation is the homomorphism. I've already said that it has restricted homomorphic properties. Now I just want to get a bit more concrete. So just as a reminder, again, we have our commitment scheme, where we have, like, in the original commitment, we commit to z times gamma to the power of -1 mod q. And then in the relaxed interpretation, it will be equal to x times z divided by gamma over the integers, rounded to the closest integer. So yeah, honest commitments are trivially homomorphic. We can just use the homomorphic, I mean, everything is equal to the original commitment scheme, so we retain all the properties up to the bound, of course, up to where x0 and x1 overflow. Also, we have homomorphicity for homomorphy for small constants. So let's just say we want to add the constant a to the committed value. Then we just commit to a and 0, and we add it with the homomorphic operation to the other commitment scheme, to the original commitment. And then if we compute the committed value, it will actually be equal to x plus a. So these two properties are very important for range proofs in the setting that, so in our setting where we need to show the 3-square decomposition. But in other setting, it might also be necessary to have dishonest homomorphy, and this actually does not work out of the get-go. So say, for example, even though the denominator is the same, we have some non-equal z0 and zi, and then if we compute what happens if we use the additive homomorphy of the original commitment scheme, then depending on how much we round before, we might or might not get a +1 in the new committed value. So essentially, in the dishonest setting, we don't retain exact homomorphicity, retain exact homomorphy. There's essentially a small error, and then it gets even worse for non-equal denominators, because yeah, you first then have to compute the you have to multiply the denominators and the denominator, and then you already get larger, and we know that we need to have shortness compared to the modulus. So this will have quite the growth, and also it's not 100% exact, as this with the same reasoning, essentially. So what I want to say with this is you need to be careful if you use this range proof, because first of all, you need to ensure that committed integers are small enough, and you need to be careful about what you actually guarantee if you use this later on in a setting. Yeah, I mean, we're working currently on a way to make this less cumbersome to deal with in applications, and it also already works quite out of the get-go if you don't need these dishonest homomorphic properties in your applications, but if you need it, you need to be careful. So the second limitation is the group size. So what we need to ensure is this square decomposition, but we can only check the size of Zi. So we need to ensure shortness for this square decomposition. And that means that Zi already has quite the overhead over Xi because we need to mask it. So we need to ensure that both sides are smaller than the modulus Q in the extraction. So this leads to large group sizes. So even though, for example, we might have a security parameter 80, we might not be able to use 160-bit groups if we don't allow for repetitions. So also something to keep in mind. And then, yeah, lastly, I just want to quickly, so yeah, I'll go over the rest of the slides a bit quicker, but I still want to get into optimizations. So essentially, as I've shown before, we need to make sure that Zi is small, and it's essentially a mask plus gamma, so the challenge times the integer xi. And what we want to show, what we want to do is we keep it short. So rejection sampling is one option where we keep the mask, where we allow for shorter masks. So essentially we sacrifice perfect completeness, but what we get is shorter masks and thus a smaller modulus. The same with repetitions. We keep the challenge shorter, so we need to mask a shorter value. Thus also we have a smaller modulus. And lastly, we can also, I mean, everything I've shown you before is interactive, but we can just apply Fiat-Charmian to the Sigma protocol and we get non-interactive range proofs. So what we want for privacy preserving technologies generally. Yes, so lastly, quickly talking about the settings where we applied it. So the first setting is the D-log setting where we improve on bulletproofs. I go into a more detailed comparison later. Then the latter setting, we constructed a range proof that is quite efficient for large batches. And then in class groups, we constructed the first concretely efficient unbounded integer commitment scheme without trusted setup. So here, all of these are, of course, without trusted setup, but this concretely is even an unbounded integer commitment scheme. Whereas in the D-log and lattice setting, we need shortness of the modulus. So quickly in the D-log setting, we have a group with prime order Q. We have G and H, so we use Pedersen commitments, so we choose G and H as random generators. This can be done without trusted setup. And then we, in order to commit to a message X in ZQ, we just choose a short opening R, so a short randomness R, and then we just compute G to the X, H to the R. And yeah, this is essentially secure, so binding and hiding under the discrete log short exponent assumption. And then for the decomposition, we just use the homomorphic properties of the commitment scheme in order to show the decomposition quite efficiently. And from this, yeah, we will get efficient range proofs for even just a single, for essentially a single integer. This is the setting where this proof shines. And then if we compare it to the currently most efficient scheme in the D-log setting, the most efficient range proof scheme in the D-log setting, then we get a proof size that's about 80 to 90% of its size. And also what's the most, or not necessarily the most, but what's quite interesting is that we have quite the improvement over provers work, so over computational work in the range proof, because we're about 6 to 12% in group multiplications. You have to keep in mind that the group that we work with is slightly larger, but still we have only a fraction of the work in group multiplications that we need to compute. So this is the D-log setting. Then
can I just ask you a quick question about the table? So these percentages, they mean that, for example, if bulletproofs take T time, then this one takes, let's say, like 12% of T. Yes. Okay.
So about 12%. So it's not time, it's in group multiplications. So if bulletproof has T group multiplications, then this has 12% of T group multiplications.
Okay.
So one time it's T. And the same for proof size. So proof size is in bytes. In bytes. So if bulletproofs has 700 bytes, then our proof will have, like, for example, about, I don't know, 560 bytes in some settings. So yeah. Then for the latter setting, what we use is BDL18 commitments. So we have a prime Q, we have a matrix A in set Q to the power of something. So this is not very important for the talk. It's just a matrix that is constructed in such a way that we can use the SAS and LWE assumption. I mean, it's a very good paper and very interesting, and I would suggest it to read it for anyone that's interesting. But yeah, for this talk, it's not that important how the matrix A is built. And then we have an integer So in order to commit to an integer, we actually commit to vectors over ZQ. So not an integer for now, but if we relax it, we can commit to integers. But just for the basic scheme, we can commit to vectors over ZQ by essentially computing the matrix R A times something short. So D sigma is a Gaussian distribution, a discrete Gaussian distribution, and then we compute A times some sample value, which is short, A times something short, plus 0 padded with, or like X padded with zeros. And this is secured based on the plain SLS and LW assumption. And then we can, in order to show the decomposition, it's a bit harder because this has slightly less homomorphic, or like slightly less strong homomorphic properties than the previous Peterson commitment scheme. But essentially, we can just use a small decomposition trick with a polynomial that is, or like we can show the decomposition with a polynomial trick that is very common in lattice literature, and then everything turns out to work perfectly fine. But yeah, we need to pay a bit of an overhead. And then yeah, essentially we perform the range proof for each component. So n we can choose freely, and then we can just prove for each component that the integer lies inside the given range. And so if we compare this to the lattice setting, so over bare LWE, we are quite efficient for small batches, and essentially our range proof scales very, very well with large batches, so a lot better than the other work. And even if we compare to the recent ring LWE schemes, we are also quite efficient. We get more efficient with a higher batch size. For small batches, it's about equal. And you have to keep in mind that here it's not that competitive as before, and you have more restricted homomorphic properties. So yeah, it might be a good idea. So, but what we did is we applied it in plain LWE. So if there's a way to also apply it in ring LWE, you might get better efficiency than this. So lastly, I want to talk a few seconds about class groups. So class groups are groups with hidden order G. We also use Peterson commitments, which are secure based on a hidden order assumption and a subgroup indistinguishably assumption. And the only way that extraction in this setting differs is that we don't extract something mod Q, but we extract an integer Z and an integer 2 to the power of L, so a power of 2. And the extracted value will be equal to X. So X, the extracted value, will be equal to Z divided by a power of 2. So this is only the case. So only if we have non-trusted setup. So if we don't rely on trusted setup, then essentially in class groups we can compute square roots over group elements. So in the exponent, this leads to dividing by 2. And this is why non-trusted setup is essentially a bit harder to work with, but our method actually applies perfectly to this because we can deal with fractions. And if we just apply the same encoding as before, and we use the same structure as the DDoc version because these are also Peterson commitments, then we essentially get a range proof for unbounded integers. So here we can commit to any integer we want for the price of having larger group elements, because these group elements you can think of like 150 bytes, whereas normal group elements in like a normal secure group that is not a class group, like a elliptic curve, you generally have like 250 bytes, something along those lines. So not 250 bytes, you only have like 8 bytes, so 250 bits around this size for a group element, and thus also for a commitment. So you pay a bit in the price of of the size of the range proof, but in turn you get you can commit to unbounded values. Yeah, and this is already it. These are the references I used if you're interested in. And yeah, now I'd be open to answer questions if anyone is interested.
Thank you very much, Michael, for your interesting talk. Maybe we can take just one question for the sake of time, if anyone has a question. Yeah, I'll ask a question. Could you go back to the previous slide?
Yes.
I'm a bit confused here. So the batch size is larger in the. So if we kind of remove the first two rows, how come the batch size is larger but the proof size is smaller for your work?
This is I should have written this. This is amortized proof size. So.
Okay.
Yeah. So essentially, the concrete proof size is 31 times 6.3 or 31 times 70.
Okay, I see. Okay. Okay.
Yeah.
Okay. Right. Yeah, I think there is no other question. Any last questions? Let me ask again. All right. So thank you very much, everyone, for your attendance. And thank you very much, Michael, for your interesting talk. Hope to see you all in the next seminar. Bye, everyone.
Thank you.